and ongoing series of off-grid system design classes and other subjects that we carry here at AEE. And today we're going to be talking about off-grid system design and system sizing parameters and the information you need to know to size an off-grid system and how that's done. And so, let's just launch into it and see how it goes here. Okay, first I want to describe what an off-grid system is, and it's a power system that has no access to the electrical grid. Typically, batteries are used to provide for loads when it's dark or cloudy and the sun isn't shining. These systems, the modules and racking are usually the same as in grid tie applications, although there are certain modules that are called off-grid modules, and we'll talk about that in a little while. But most of the components are rather specialized for off-grid situations. So they're very different than grid tie systems without batteries. So there are a variety of different types of off-grid systems. One of the simplest is either solar PV or wind direct systems, where the loads are run directly from the renewable energy source. There's generally no batteries in those systems. As a matter of fact, that by definition there's no batteries. Loads typically are motors that run directly from the energy source, so it might be fans or pumps or circulators or that kind of thing. Sun comes up, hits the PV, provides power, the load runs, sun goes down, the load stops. So it's just based on daytime use, often at variable speeds depending on the intensity of the sunlight. Then there are systems that are just running DC loads. These might be simple lighting systems or something like that. There are batteries involved in that, but no inverters. Just DC, might be 12 volt or 24 or even 48 volt DC loads. Then there are systems that are AC only, where all the loads are run off an inverter or a generator. And these are the most common types of off-grid systems used for homes. I mean, in the old days, we used to wire homes both for AC and DC because many DC appliances, such as lighting, were much more expensive, much more efficient than their AC counterparts. But these days, really, AC only is pretty much the way to go, especially with LED lighting and other high-efficiency loads. Then there are systems that do have both AC and DC. It's still common in things like recreational vehicles or boats, marine applications, a lot of places where there may be some DC loads but also AC loads together. And then what we call hybrid systems, which are systems that derive their energy from more than one source. So it might be PV with a wind turbine, or PV in the utility grid, or PV in a generator, or PV in a hydroelectric, or PV in a fuel cell. I mean, some sort of hybrid that is having more than one source of energy. So, what is the difference between an off-grid system design and a grid tie system design? Well, there are some basic differences to keep in mind here. In a grid tie system, and we're discussing a net metered system here that's done on a yearly basis. There are certainly other types of net metering and other types of grid tie systems, but most of the country is on net metered grid tie. So in a grid tie system in that situation, the energy production is based on the yearly consumption. So the size of the system is based on offsetting what the yearly consumption of energy is. In an off-grid system, the energy has to be produced on a daily or weekly basis. It's not based on a year's time, but on really very short period usage, because you can only store energy in batteries for a short period of time, basically. In a grid tie system, some energy is used directly as it's produced, and some energy is sent to the grid. So you're running your meter backwards, and that extra energy is stored as credit. In an off-grid system, you might use some of the energy directly during the day, but also some of the energy is stored in batteries. So it's not credit, it's actually energy stored as chemical energy in a battery. In a grid tie system, the PV array size is based on the yearly energy production of the PV array to offset a yearly amount of kilowatt hours from the utility. In an off-grid system, the PV array is sized based on the energy production during the darkest time of the year. Since again you're working more on a daily or weekly basis, you have to size your system for the least amount of energy production, essentially, that you get, which is typically in the winter in the United States. In a grid tie system, the inverter is sized to match the PV array. So if you have a 6 kilowatt PV array, you need a 6 kilowatt inverter. In an off-grid system, the inverter is only sized to run the peak AC load, not the array size. So you might have a 4 kilowatt inverter with a 2 kilowatt array, or a 4 kilowatt inverter with a 20 kilowatt array. It doesn't really matter. The inverter is sized to run the loads. The array is sized to produce the energy to run those loads over a period of time. Grid-tie systems are rather simple. There's only a few components. It's racking, modules, and inverter, a little bit of switchgear, pretty simple. Off-grid systems are often very complex with many components, with charge controllers and different switchgear and metering systems. Definitely a lot more complex than grid-tie. And in a grid-tie system, if the system does fail, the lights still stay on. And you'll probably get a call on Monday morning that there's something wrong with the system, or you may not get a call for a month when they get a higher electric bill from the utility company, but the lights are still running. In an off-grid system, if the system fails, the lights go out, and you'll get that call on Sunday morning instead of Monday morning. So be aware of that you become the energy company for your customer. Should they have problems in an off-grid system, that the installer is likely the first person that they're going to call. So when you're doing off-grid system sizing, you have to remember that the purpose of the system is to provide power to run loads. We're not just producing kilowatt hours of energy here, we're actually producing power to run loads. So the first place to start is to do analysis of the loads. We need to know what loads we need to power in order to properly size the system. So here's some of the information you need to collect before doing a system design. We need to know what the daily power consumption is, daily energy consumption. How much energy will the application consume each day? Is that seasonal? We need to know the winter consumption, the summer consumption, spring and fall, if there's a lot of variation in particular. For each load, we need to multiply the power draw of that load by the hours is used per day to figure out the kilowatt hour consumption per day. Appliances such as refrigerators and freezers are best done by finding their Energy Star consumption number and dividing that by 365 to get a daily average consumption. We need to know what the peak load is and what the characteristics of the power are. So is it a DC load, an AC load? If it's AC, is it 120 or 240? Is it 50 hertz or 60 hertz? These kind of things we need to know before we can size the system. So we need to add the sum of all the loads run simultaneously. So the inverter has to power many loads at the same time. So for instance, maybe a well pump and a washing machine or something like that are going to run at the same time. We need to know that to be able to size the inverter. We need to know if there's separate AC or DC loads and what the voltage and frequency is that the loads require. We need to get some idea of the days of autonomy, or how much energy storage we have to carry over of periods of time where we don't have a lot of sunlight or other types of energy production. And this is mostly used to size the battery at that point. And don't forget to account for things like heavy snow cover of PV modules and blocking the sunlight and therefore needing more from the battery. And then we need to know about the site and what the sun hours per day are during the darkest month of the year at that site. And generally, again, with off-grid, we use the winter time. It says winter solstice here, but we use the winter time figures because we need to look at the worst case scenario of being able to produce enough energy to run the loads in the house or building. And usually if we size for the winter, we'll have excess power in the summertime, but that's okay. I mean, it's certainly better to have too much than too little. So starting with a load analysis, the first thing to do is work up a list, sheet. Now we do have a load worksheet in our catalog, in the beginning section of the catalog, that can act as a template for doing this. We also have it in an Excel form that we can send you, which is much easier to fill out. But essentially, we're describing what the load is, how many watts it takes, how many hours per week it's run. And we use a weekly and then divide by 7 so we can get an average for the day, because not every load may be run every day. So we generally look at a week and then divide by 7 at that point. One thing to consider when you're doing load calculations is that there are things called phantom loads, and these are items that appear to be turned off, but they still draw some energy. And we need to account for that because it can actually add up to quite a bit. This is a list here that was produced by the California Energy Commission and the U.S. Department of Energy of just some common household items that, even when turned off, draw energy. And as you can see from this list, that should you have this whole list in a house, that's about 123 watts of power. Which is almost 3 kilowatt hours a day just to run things that are essentially not being used. So one of the ways to deal with that is to put many of these on switched outlets or on plug strips. So even though you turn them off, you can actually switch the power off to them. This is particularly useful for things like televisions and things like that. Some of these items you can't do that with because they have programming that will be lost. So some of these are going to be phantom loads. You just have to account for that, and there's really no way to get around that. But just be aware that those exist in a house. So here's an example of our Excel spreadsheet load analysis form with some numbers filled in as just an example. And I'm going to use this example through this presentation so we can actually work with some real numbers rather than just hypothetical numbers here. So you can see from this list showing that peak wattage is 4,934 watts. That's if all of these appliances or loads were run all at the same time. You would have a draw of roughly 5 kilowatts. It's not likely all of these are going to run at the same time, but there's certainly a possibility that they can. And that ends up being a daily kilowatt hour consumption, or watt hour consumption, excuse me, of 7,432 watt hours per day on average. Again, if you look at the chart here, for instance, the first one, the furnace blower, is only listed as 5 hours a week in this case. So it's not everything running 24 hours, but the accumulated usage per day is an average of about 7.5 kilowatt hours. We have to adjust that because of inverter inefficiencies and system losses. We use an 87% figure here, which is pretty conservative. Most modern battery inverters are more like 90 to 92% efficient these days, but there are also other losses in the system, such as wiring losses. So we want to account for that and be a little conservative here. So we actually come up with a figure of about 8.5 kilowatt hours a day, 8,543 kilowatt hours in a day. It's the actual energy drawn from the battery, even though the loads are only consuming about 7.4 kilowatt hours. And again, our peak load is just about 5 kilowatts. So we really want to size this for a 5 kilowatt inverter to be able to run all those loads at once. So it looks like there was an audio glitch. So yeah, with about 5 kilowatt load, we really want to use a 5 kilowatt inverter. It's certainly possible for the owner to load manage and not run too many things at the same time. A 4 kilowatt inverter would probably work fine in this application, but that really depends on the customer. Is the customer very energy conscious and willing to manage their loads, or do they just want to be like downtown and run everything at once? I think for the most part, it's really better to just have an inverter that's big enough for the worst case scenario of all these things running. They may have guests, for instance, that don't know about the energy consumption issues and that kind of thing. So we really need to design a system that's going to work for them all the time and not really be a problem for them. So after we've done our load analysis, then we have to do a site analysis. We have to see what the solar energy potential is at the site, or whether there are other potential energy sources other than PV. Again, with the solar, you have to size the system based on the peak sun hours during the darkest month of the year, not the yearly average. We need to know about shade issues, mounting space. Most off-grid systems are rural, so mounting space is not usually a problem. The PV array doesn't have to be on the roof. It could be a ground mount, but there might be a lot of trees or other things, obstructions. We need to know that. And we need to know if there's any possible other energy sources, such as a wind potential or micro hydro potential. Wind and hydro turbines can produce power when sunlight's not there, so they can, really improve the energy production reliability of an off-grid system. It's really a great addition. Very often when the sun is not shining, the wind is blowing, or the water is flowing, and if we can capture that energy, we can smooth out our production curve, and we can have a much more reliable system. Then we need to know some basic weather data of the site. How many cloudy days in a row should we design for? Where I am in Northern California, I've seen it rain for a month solid. It's not really possible on a solar-only system to store enough energy for a whole month. It's certainly not cost-effective. So there is going to have to be some additional backup, typically a generator. And most off-grid systems do require some sort of backup. Even if it's only used 1 or 2 days a year, it's pretty hard to have 100% solar in most locations. Southwest desert might be an exception to that, but in most locations in the U.S., you will need a backup generator. So doing PV array sizing, we need to know what the peak sun hours are at the site. There's a number of sources for gathering that information. The good old NREL Red Book, which was 30 years of data for a couple hundred places in the U.S. It was the primary source. We also have maps in the back of the AEE catalog. These maps are, show sunlight potential or peak sun hours during the darkest month of the year all over the world. This is not the yearly average, it's the darkest month. So these maps are useful for sizing off-grid systems, but not useful for sizing grid tie, where you're looking at a yearly average and not the darkest month. But probably the best way to do it is to use PV-Watt, which is the online calculator from the National Renewable Energy Lab. This is a screenshot from the first version of PV-Watts. They have the second version up, which is even more useful. But I use this, just to show the numbers here for a particular location. In this case, this is Knoxville, Tennessee. And as you can see from the chart, it's showing a yearly average peak sun hours at 4.66, but in December of only 3.22. So that's about an hour and a half less peak sun in December than the yearly average. And that's why we need to look at wintertime energy production and not just the yearly average with a grid tie system. With an off-grid system. Now, obviously, if it's a seasonal off-grid and it's not used in the winter, it's only a summer occupancy, like a vacation cabin, then we would size it for that time of year. But if it's year-round use, like a household, we need to look at the wintertime use, and that's really important in the design calculation. So figuring out our PV array size, we know from our analysis that we need to produce 8,533 watt-hours a day, roughly 8.5 kilowatt-hours a day. We multiply that by 1.25, and that factor accounts for charge-discharge efficiency losses over the life of the battery. When batteries are new, they're fairly efficient, typically 92 to 94% efficient, but as they age, their efficiency goes down. So we need to account for being able to produce enough energy over the lifespan of the battery. So we generally use a figure of 1.25, which is fairly conservative, but we want to overestimate, if anything, rather than underestimate. So even though our consumption shows roughly 8.5 kilowatt-hours, we actually need to produce about 10.5 kilowatt-hours of energy in order to make that up and refill our battery and be ready for the next cycle. Pretty important number to do that, to make sure you calculate the losses in. So assuming that we have to produce 10,667 watt-hours a day, and we are sizing for December, which is 3.22 peak sun hours in Knoxville, Tennessee, we need a minimum of 3,313 watts, PV watts, to be able to do that. And again, that's a minimum. So if we choose, for instance, a 280 watt PV module, we can divide that number by 280 watts, and it tells us we need 11.83 modules. Well, obviously, we're going to round up to 12 at that point. So the design is calling, in this case, for 12 PV modules rated at 280 watts each. However, going to 15 would certainly make the system more reliable and further reduce the generator time. It would get you through cloudy weather, because remember, even the 3.22 sun hour figure for December is an average for that month. It's not necessarily what you're going to get in a day. Some days you're going to produce almost nothing if it's very dark and rainy. Other days where it's clear and sunny, even in December, it's probably more like 5 peak sun hours. So it just averages out to 3.22. By adding more modules to the system, excuse me, we can, overcome that cloudy weather. First of all, it's going to produce more energy in low light. It's also going to produce more energy on a sunny day. It just makes it more reliable. And in this example, I'm going from 12 to 15 just because with most of the solar charge controllers that are on the market these days, they're rated at 150 volt maximum. So typically you use 3 standard 60 cell modules in series for a 48 volt system. So the number of modules really needs to be in multiples of 3. So you can do 9, 12, 15, or 18, but not 16, for instance, with those charge controllers. There are some controllers that do different voltages, either higher or lower, but generally we use standard modules in groups of 3 with these off-grid designs. So then we need to look at our battery bank sizing. Now that we've sized our PV array, and back to the loads, we're consuming roughly 8,533 watts. And if we divide that by the battery voltage, in this example I'm using 48 volt, which is going to be the most common for home setups, we come to a figure of roughly 178 amp hours per day. That's going to be the consumption out of the battery. Now, in sunny winter areas where you don't have long periods of cloudy weather, we typically size to have 2 days of energy storage to a 50% discharge point on the batteries. And I'm talking mostly about lead acid batteries here because they're still really the standard by which we go by. Other technologies coming forward, such as lithium ion or saltwater batteries, you can generally discharge them further without shortening their life much. So these figures may change a little for that, but still, you still, in an off-grid system, you still want to be able to store energy. It's not just based on cycle life or depth of discharge. You still want to have energy available to run the loads in the house. So in a sunny winter area where you're getting lots of sunlight even in the winter time, you don't need a whole lot of storage because you don't have a whole lot of cloudy days. So in that case, we typically look for 2 days of energy storage, so 50% depth of discharge, which essentially means that by the rating of the battery that we have 4 days, because 2 days to 50%, it's 4 days to 100% on the rating of the battery. So we would take the 178 amp hour multiplied by 4. That gives us a number of 712 amp hours. That would be the minimum battery bank that we should be looking at for this system. In a dark winter area, might be the Pacific Northwest or the Northeast, other areas that have long periods of cloudy weather, we're going to want more storage than that. So we typically size to 3 days of storage to a 50% depth of discharge, which essentially means the daily draw multiplied by 6. So in this case, we come up with a 1,068 amp hour battery bank. So, just looking at this, if you were in, say, Phoenix, a 700, 750 amp hour battery bank would be a good minimum size for this system. If you were in the Pacific Northwest, you'd want to up that more to like 1,000, 1,100, 1,200 amp hour battery bank, somewhere in there, to be able to have more storage to get you through more cloudy weather. So here's kind of the results of doing all that. Load analysis told us that the inverter needed to be rated for 5,000 watts of output power. Again, a 4,000 watt inverter might be okay in this situation, excuse me, assuming that people could load manage, not run too many loads at once. You really have to kind of feel out your customer and see if they want that. Some people are moving from the city to the country and they don't want to even think about it. They want to be able to run what they want to run when they want to run it. Another thing I'll point out is that generally when you do this analysis, there's a lot of guesswork involved. you're guessing in how many hours a particular load is going to run. And from my experience, at least, I've seen that once people establish a system, they tend to add loads over time. So you want to design the system to be expandable, or at least even have it larger than the original design states to allow them some room for expansion, to maybe add a freezer, for instance, that they don't have, or some other kind of load. So you want to make sure that you can not only accomplish what needs to be done in terms of your system sizing at the moment, but be able to do that also for future use. So it's a 5,000 watt inverter, you actually might use a 6,800 watt inverter, or even an 8,000 watt inverter in this situation, to be able to allow them to expand into the future and have a system that's going to work for them for the next 15 or 20 years. The load analysis also told us that the loads, including the inverter losses, consumed about 8.5 kilowatt hours a day. The site analysis told us that we needed to size the PV array for 3.22 peak sun hours in that location in the wintertime. The combination of the load and site analysis, the results of the 8533 watt hours and the 3.22 peak sun hours, times the 1.5, told us the minimum array needed was 3,313 watts. The array PV watts divided by the module wattage told us we needed about 12 280 watt modules. The energy consumption told us that we would have a daily draw from the battery of roughly 178 amp hours. And the daily consumption times the number of days of autonomy told us that the battery bank rating should be somewhere between 700 and 1,200 amp hours, depending on the location, the length of winter storms, the periods of time that you need to store energy in a battery, you don't have production. Now, if you did have a wind turbine or a hydro turbine added to the system, you could probably reduce those battery numbers, because you would likely have more energy production at night or on cloudy weather, when it's raining, that kind of thing. So you have to play with these numbers based on the actual situation at the site. And so it's really important to do that kind of assessment so you know what your total energy production is. Batteries are pretty expensive, so if we can get a situation where we can produce more energy more of the time and reduce our storage requirements, that's also always going to be an economical thing to do. So pretty important to do there. So then when you're designing the system, now that we have the numbers, we know how big the system needs to be, we need to make some decisions on the types of equipment that we're going to use in that system. So we need to decide whether we're going to use flooded batteries or sealed AGM or gel lead acid batteries, or some advanced battery design like lithium or salt water. We need to consider what the maintenance requirements are for these, whether the customer can do the maintenance or is willing to do the maintenance, or whether we need to do a service contract with that customer to maintain the system for them. We need to be aware of shipping, handling, and storage requirements. For instance, I'm working on a project right now where the only access to the location is by canoe. In that situation, I am not going to specify a 500-pound battery that's going to go in that canoe. We have to have, smaller, lighter batteries, maybe more of them. It may not be ideal even, but because of the transportation issue, we certainly have to be aware of that and choose the equipment wisely for that purpose. We need to decide our battery bank voltage. Now, 48 volts is really pretty much the standard for just about all systems, at least systems over about 2 kilowatts of PV. It's not real cost effective to do a lower voltage once you get over about 2 kilowatts. So for instance, a typical 80 amp charge controller will do roughly 2 kilowatts of PV modules at 24 volts. But it'll do 4 kilowatts at 48 volts. So if you only had systems or outdoor lighting, some small systems like that. Billboard lighting, for instance, might be lower voltage. We need to choose our charge controller type. There are two basic types of charge controls. The simplest and the oldest type done is called pulse width modulated. It's basically, solar panel connected, solar panel disconnected. It's an on-off controller, but it does that disconnection point at variable speeds depending on the charge to the battery. So it'll have more or less time of the PV connected to the battery to charge the battery. And it controls the battery by high-speed switching of the PV array. Actually fairly simple circuits, but they do require that the PV array that the voltage of the PV array somewhat match the voltage of the battery. They have a nominal rating on it. So 12-volt modules are made to charge 12-volt batteries. They have 36 cells in them. 24-volt modules will charge 24-volt batteries, and they have 72 cells in them. There aren't any 48-volt modules really on the market, although some of the thin film modules are pretty close in voltage characteristics to 48-volt to be used with a PWM controller. But generally, most of the modern modules are 60-cell modules, which are not matched to a nominal rating of the battery. So with those, you need to use a maximum power point tracking charge controller. Which will allow the PV array to operate a higher voltage battery bank and convert that higher voltage into more charging amperage at battery voltage. So maximum power point tracking can be used for arrays. They could be up to 150 volts or 200 or 250 or even up to 600 volts DC and still charge a battery, typically 48 volts. Most of these charge controllers can also charge 24-volt batteries. Some of them can charge 12-volt batteries. And there's some advantages of these. Now, if you have a charge controller that does 150 volts with a typical 60-cell module in the 280, 300-watt class, you can use 3 in series. With a charge controller that goes up to 200 volts, you can typically use 4 of those modules in series. Up to 250 volts, you can typically use 5 of those modules in series. Now, obviously, when you're putting them in series, you're increasing the voltage. You can run greater distances on smaller wire, so you may want to do that if your PV array needs to be a longer distance from your battery bank. And then there are some manufacturers that make 600-volt charge controllers, where you're basically doing strings of modules very similar to what you would do with a 600-volt grid tie application. It might be 12, 13, or even 14 modules in series in that case. And you can run very long distances with very small wire in that case to be able to have a PV array 300 or even 400 feet away from the battery bank. And then you're choosing your module type. Obviously, 60-cell modules are really dominate the market. They're going to be the cheapest price point. About the largest that you can have that's easy to handle. 36-cell modules are still made and useful for very small systems at 12 or 24 volts. 72-cell modules are these days mostly used for industrial and large commercial systems, but they can certainly be used in off-grid also. They're a little heavier and harder to handle, but they can be used. If you're using 72-cell modules, 150-volt charge controller, you can only do 2 in series, so you would have pairs in that case instead of that's 3 with 60-cell module. So you do have to consider mounting limitations and transportation when you're choosing your modules. Obviously, the 36-cell modules are smaller and lighter, easier to handle, easier to get on a canoe, for instance. 60-cell module might be a little more difficult for that, but is going to be a much cheaper cost per watt in general because it's much more mass production. So here's just a basic diagram of an off-grid system. This is out of our catalog, actually. And if you can see here, we have a PV array. In this case, we just have 6 modules shown, but they're in 2 strings of 3 for a 150-volt charge controller. The output of each of those 2 strings go into a combiner box, which has either fuses or breakers that for each string that then combine them into a single PV output circuit, which then goes down to this green line here is the DC power center. So These systems are going to have a power center of some sort, a power panel of some sort that's going to have all the AC and DC switchgear for the inverter and the PV modules and the house loads. And there are a variety of manufacturers that make those. But the PV output is going to, first land on a PV input circuit breaker, then go through a charge controller, have a breaker on the output of the charge controller, and connect then to the battery, but connects to a DC bus inside the power center, which then connects to the battery. So the energy is flowing from the PV through the charge controller, through overcurrent devices and switchgear, and going on to the battery to charge the battery. It's not going through the inverter system like it is with a grid-tie system. So this is a major difference in off-grid systems. So then once the energy is in the battery, it can be drawn out of the battery through a circuit breaker to the inverter. And at that point, the inverter can then power a load center, all the AC loads on it. A generator input would be inputted into the inverter as an AC source. The inverter, most of the inverters that operate for off-grid systems have internal transfer relays. So the generator goes to its own transfer switch, powers the load at that point when the generator is running, and the inverter basically turns into a battery charger and can use a portion of that generator's power to run backwards here and charge the batteries. So as the generator is running, the batteries are charging and the loads are being run off the generator. So it's important to have a generator that's large enough to do both functions at once. The inverters can be adjusted for how much of the generator energy they're using to charge batteries. So if you need to run big loads, you might have to turn down the battery charging on the inverter in order to use more of the generator's power if the generator is somewhat limited there. And then when the generator is switched off or runs out of fuel or for some reason shuts off, the inverter will automatically switch back to drawing energy from the batteries and powering loads in that case. And then if you have any other kind of inputs, wind or hydroelectric solar input, they're basically just combined in the same way that another PV array would be combined, also going through a DC breaker, through some sort of charge mechanism. Some wind turbines have built-in charge controllers, some need external charge controllers, depends on the brand. Hydroelectric units generally need external charge controllers. So it's just another source, charging the battery, connected to the DC bus and charging the battery at that point. But everything that is connected to the battery must go through a DC-rated circuit breaker rated for the voltage of the system that it's operating on. Batteries can dump enormous amounts of current into short circuits and melt things and start fires. So every connection to the battery needs to be have overcurrent protection on it. Most of these systems are negatively grounded, so the overcurrent protection is in the positive lines. There's very few positive grounded systems. Some, mountaintop telecom communications gear is positively grounded, but for most homes we have negative ground systems, so all the overcurrent devices are in the positive terminals. So that's a basic overview of a system. In some future webinars, we will go through and discuss each one of these components in more detail and be able to show you variations in the different brands and models and what they can do and how they function. So, do we have any questions coming in?
All right, thanks, Brian. Yeah, we've got quite a few questions here that are looking really good. So we'll just go ahead and get started here.
I figured there would be.
Yep. Yep, it's been nonstop. So we'll go ahead and get started right away.
Okay.
Let's see. I'm putting a PV system in batteries, but tying into the generator. Can I program the generator to kick in when the batteries get to be below a certain percent?
Yes, actually most of the systems are not really based on percentage, they're based on this battery voltage. The inverters these days have built-in what they call auxiliary relays that can be programmed for different voltage points. So when the battery voltage drops to a certain point, and there's time delays built into these kind of things too, because when you put big loads on batteries, the voltage drops. You don't want the generator kicking on every time the washing machine goes on, for instance. But there are relays that can do that. They can automatically start the generator based on battery voltage. There are a few systems that also use amperage or battery capacity calculations in their equipment that can be programmed to do that. So yeah, it can certainly be automated to the point where if your PV or other renewable energy sources aren't keeping your battery topped up enough, battery voltage drops to a certain point and the battery capacity drops to a certain point, that the generator can be automatically started. One caveat with that is it's really important that people like check the oil in the generator. Most generators have, automatic shutdown on low oil, high temperature or something. It's important to not just think that an engine powered generator can just go on and off without any service. I often find with automated systems that people kind of forget to do service on the generator. So, but yeah, basic answer to the question, yeah, the systems can be programmed to have automatic generator start. There are even separate standalone modules that can be used to automatically start generators. Now the thing is, the generator has to be set up for remote starting. If it's the type of generator where you have to go out and you have to switch it on, you have to pull a cord, that's not a remote start generator. So you're going to have to do that manually. Even an electric start generator is not necessarily set up for remote start, because it would also have to have an electric choke, for instance, rather than a manual choke. So, make sure if you want to automate the system, make sure that the generator itself is set up for remote starting to do that. And then, yeah, there is equipment to automatically start them.
All right, great. We'll lead into our next question. In your peak load calculation, how do you allow for the surge when some appliances start, such as the fridge or the pump?
Okay, that's an important point. You do have to allow for surge, especially for big items like pumps or compressors. Most of the inverters will surge to up to twice their rating. So typically if you had, say, a 6 kilowatt inverter, you can typically get 10 to 12 kilowatts of surge power for up to 5 seconds. So really the inverters are pretty much designed to handle that. You certainly have to make sure that your battery is large enough to be able to deliver that kind of surge also. You don't want a very small battery that you're trying to draw a huge amount of power out of. But certainly, yeah, if you have big loads that have big surges, you do need to keep that in mind, that you need to have an inverter big enough to handle those surge loads. And again, most inverters can handle some pretty good surges and take care of that. Hello, I don't know if we lost Ham.
All right, yep, sorry about that. We'll move on to our next question. Is there a different battery efficiency multiplier for different battery technologies?
That's a good question. I think they're all fairly much in the same place. I mean, even lithium is in the maybe mid to lower 90% efficiencies. The aqua and saltwater batteries are pretty much in that realm. Doesn't seem to be a whole lot of difference in the efficiency of the batteries at this point. Essentially, you take a certain amount of energy out of a battery, you have to put more energy in to get it full again. And that energy is typically lost as heat inside the battery. So, again, when batteries are new, they're pretty efficient, but as they age, their efficiency goes down because their internal resistances change. And more of the charging energy is going to be produced as heat rather than as a chemical composition. So all the batteries are pretty much in the same realm. I mean, certainly you're going to want to look at a particular battery technology you're using and see what the efficiencies are, and you can maybe adjust your figures to that. But one thing about all this design is, again, there's a lot of guesswork involved here, and you want to opt to the higher end. So I think it's always good to be conservative on these kind of designs and basically figure more inefficiency in than you may have, but you don't want to be so tight in your design that you're looking at a certain exact efficiency, with just a couple % differences. You want to have a little more padding than that.
All right. The next question we have, how would you design a system for an RV with a 50 amp outlet?
Well, this is something that comes up from time to time. The idea of a 50 amp outlet is an idea that there's unlimited energy there. And really, we can't just look at, you know, a 100 amp service panel or a 125 amp service panel or a 50 amp service panel and just design to that. We really need to look at what the loads are. Yeah, I mean, we can design for 50 amp, but we're going to end up with a system that's probably a lot larger and a lot more expensive than you actually use. So looking at actual usage and not the rating of the input is important from a cost perspective, and also a space. Obviously, you know, huge arrays or huge battery banks take up more space. So we really want to look at the loads and not just what the source is. Now, most of the inverters have built-in transfer switches, and most of them are rated for either 30, 50, or 60 amps. And so when you're connected to, for instance, shore power on an RV, you need to be able to have overcurrent protection of that inverter. You're not overloading the internal transfer switches. So it might be an inverter with a 50 amp transfer switch. You're fine connecting to a 50 amp service at that point. If it only has a 30 amp transfer switch, you're going to want to downgrade that service to a 30 amp breaker to protect that switch.
All right. Thanks, Brian. The next question we have, do you have any guidance for a seasonal cabin application?
Seasonal cabins, well, it depends on the season, of course. If it's the winter season, like a ski cabin or something, you're pretty much designing for that period of the year. If it's a summer use only, then you can really look at the peak sun hours for when it's being used and figure that there's less energy. However, you also want to keep your batteries charged over the winter. I mean, if there's no occupancy for, say, 6 months of the year over the winter, you want to make sure that there's some charging on your batteries. You don't want your batteries to be just sitting there with no charge. They may be prone to freezing. Certainly, lead-acid batteries are damaged if they're left in partial states of charge for long periods. So you want to have some charging there. And then that can be an issue if you have, you know, 8 feet of snow cover, for instance. I would recommend in that situation to mount at least some of the PV at a 90-degree angle, like on a wall. It's obviously not optimal for energy production, but it's less likely to build up snow in front of it, and at least you'll get some charge on the battery at that point in time. But yeah, cabins and whatnot that are used periodically, might be a weekend use and you have all week to charge up. You could probably use a smaller PV array and even a smaller battery on that. You're just going to have to factor those things in when you're doing your system design.
Great. That was a good question. The next one we have, will there be an off-grid solution using AC modules as they enter the marketplace?
Well, that's interesting. You know, another type of off-grid system that I didn't really talk about in this presentation is essentially an AC coupled system for off-grid, where you have PV modules with an AC, essentially a grid tie inverter, and it could be microinverters, it could be full-size string inverters, and they connect to a battery inverter. You essentially have 2 inverters in this system on the AC side rather than DC coupled at the battery through charge controllers. That'll be the subject of another webinar. But yeah, I mean, even now with something like N-phase inverters, it's certainly possible to use them in off-grid applications and AC coupled. N-phase hems and haws about whether they like that. It does wear on their internal switching mechanisms more than they do in a grid tie application, and I think there's a problem potentially with their lifespan at that point. But I certainly think that that's certainly a possibility. N-phase is also working on a battery system, which is interesting in the sense that essentially they're creating an AC battery. Where they'll have a battery that will have its own microinverter on it, and then you could have PV with microinverters, and it's all AC coupled in that system. What they've designed so far is really designed for load shaving and backup systems on grid-connected homes. They're not really aiming at the off-grid market yet, but I think that technology has some incredible potential in the future. If we had, for instance, battery microinverters, you could have batteries that are different ages, that are different sizes, that have different technologies. It wouldn't matter because they're all bused and coupled together on the AC side. So you could add new batteries to old batteries. You could have big batteries and little batteries. You could maybe even take a couple batteries out for the weekend on your camping trip and have AC power. It's an interesting idea that I think is just in the beginning of development, but we hope to see more of that. Good question.
All right. The next question we have, what if more loads are on than what the system was designed to support? Will there be voltage sag, system shutdown?
Yeah, generally the inverters are pretty good at keeping the voltage up even when they're overloaded. But what happens is that they overheat. So that, a 4 kilowatt inverter, for instance, will run, it's designed, at least according to their specs, to run 4 kilowatts 24/7. That's typically based on, 25 degrees centigrade, ambient temperature, 77 Fahrenheit. If it's a warmer room or warmer climate, it's not going to run that 24/7 at 4 kilowatts. If you're trying to run 5 kilowatts on a 4 kilowatt inverter, it will do that for a period of time, maybe only a minute or two, or maybe 5 minutes. Eventually, the internal components will overheat, and the inverter will go through a shutdown. It'll shut itself off based on thermal issues. It won't kill the inverter. You do have a blackout at that point. And certainly heat is not a good thing for any kind of electronics. So if you're doing that on a constant basis, you are going to shorten the lifespan of the inverter. Many of the inverters out now, you can hook up multiple inverters in parallel. So if you're running into a situation where, say, somebody had a 4 kilowatt inverter and they added more loads, it's not keeping up anymore, you can typically add another inverter to that system and beef up the system. Second inverter will need a second set of cables to the battery, and you may need larger batteries at that point because you have larger loads. But yeah, essentially what happens, see, in the grid tie setup, if you have a 4 kilowatt grid tie inverter and you put 5 or 6 kilowatts of PV, the inverter just limits it to 4 kilowatts and doesn't use the additional power. In an off-grid situation, the inverter will try to power those loads up to the point where it just overheats itself and shuts off. So, be aware of that. You don't want your customers calling you on Sunday morning because their power's not out.
All right. Great question. The next one we have is a question, when you were doing the MPPT charge controller calculation, are you using VMPP or VOC?
Good question. You use both, actually. You have to use the VOC when you're looking at the limits of the charge controller. Most of the 150 volt charge controllers out there will actually stop operating at about 140 volt DC, and they can be damaged if voltage is over 150 volt DC. There's a couple of units out there that can go above that. They won't operate, but they're not damaged above the 150 volts. So yeah, when you're doing your sizing on that, you have to look at the VOC, the open circuit voltage of the day, and you have to figure for the coldest possible application, which will be a cold morning before the sun has hit the PV modules and warm them up. That's going to be when you're going to have the highest open circuit voltage. You want to make sure that that stays on 50. If you have that kind of cold situation for any length of time during the day, you want that to be below 140. Otherwise, your charge controller is not going to work. Then you need to use the maximum power point voltage, the VMP, in calculating the actual system running, and that's for your wire sizing. So if your array is 150 feet away and you're sizing your voltage drop on your lines, you're going to use your VMP at that point. So 3 modules in series, for instance, should be running at about 90 volts. In hot weather, it might be 80 volts. So you need to keep that in mind when you're doing your wiring calculations. But it's the open circuit that we're concerned about with the 150 volt limit.
All right. Thanks, Brian. The next question we have, what's the max number of battery strings you suggest?
Another good question. I do not suggest going over, and again, we're talking lead acid here. I do not suggest going over 3. 3 strings in parallel is really the maximum that you should design for as a design point. And even 3 strings is a little questionable. By far, the best application is a single string of cells. And the reason for that is when you have a single string, all of the energy, the electron flow essentially, has to go through that string, either just in discharge or as charge. All the energy goes through one circuit in that string. So even if there are a few cells in that string that are a little weaker than other cells, the energy has to flow through them in an even amount. And generally, single string applications, the batteries are going to last longest. As soon as you put 2 strings in parallel, you have 2 parallel paths for current. So if one battery is a little stronger than the other battery is, electricity is going to take the path of least resistance. So you're going to end up with one string being both charged and discharged more than the other string. And that creates imbalances within the battery bank itself, and is going to shorten the life of both the good string and the bad string, essentially, because one's going to be used heavier than the other, one's going to be charged more fully than the other. You just have imbalance problems. We do have processes to equalize battery banks where you do a controlled overcharge to bring weak cells up to a higher state of charge to match the stronger cells, and that helps quite a bit. So 2 strings, you already start to see some issues. You have some loss of the lifespan of the battery, although it's generally pretty acceptable. 3 strings is increasing that even more, but it's still considered an acceptable amount. By the time you get to 4 strings, it becomes really hard to keep all the strings evenly balanced, and you have really shortened battery life. There are ways to do more than 3 strings. Big industrial or telecom applications often have many more than 3 strings, and what they do there is they have a central, like a big wall-mounted bus bars running individual cables from each string, and those cables have to be the exact same length, the same resistance characteristics to those bus bars, rather than just daisy chaining a set of strings. And that helps to balance the strings, but it's still not ideal. The ideal to aim at is 1 string of batteries. 2 is still really good. 3 is acceptable. 4, not so much. If you need to go to 4, basically you need to use a larger battery and use fewer strings of a larger battery rather than many strings of a smaller battery. And that's a pretty complex subject, maybe, and we'll do a whole battery webinar at some point and maybe explain that in more detail.
All right. Well, thank you, Brian. That concludes our Q&A portion of the webinar. Thanks, everyone, for submitting these great questions. And I'm sorry if we didn't get to yours. But, reach out to Brian if you have any other questions. And don't forget that we answer a lot of these questions on our monthly podcast, Rooftops and Wrenches. So be sure to keep an eye out for those and check them out. You should be able to find it either on Stitcher or iTunes. So look that up. We'll be covering off-grid system design in our next podcast. So should be a really good follow-up. And our next webinar will actually be in November. So November 11th will be the next webinar. It'll be NEC 2017 Sneak Peek. That should be a really interesting one. We'll have Brad Bassett presenting on that one. Don't forget, everyone, to complete that survey. If you complete the survey, I'll send you your NAPSEP certificate if you attended the entire presentation, as well as the presentation slides and a webinar-only promo. And if you missed part of the webinar or you have someone on your team who you think would be interested in listening, we will be uploading the recording to our YouTube channel. It's AEE Solar. So just type that in, look it up, and you should find this presentation as well as our other past webinars. All right. Well, thank you so much, everyone, and thank you, Brian.
Well, thank you, Hannah, and thanks, everyone, for joining. And, yeah, you can contact me. I have my contact information on this slide, and you can get a copy of this presentation also. have it in your records. Thanks for joining.
All right. Have a great weekend, everyone. And thank you for doing business with AEE Solar.